Well, sorry about that. Take 2 or take 3. Good morning, good afternoon, and good evening, and welcome to the second webinar in this series of Bayesian applications in CMC. Fan and I are happy that you join us again. And today we're going to get into the examples. I'm going to turn my camera off to improve the bandwidth here. And let's get going.
Did we lose you again, Jose?
No, I'm here. Can you hear me?
Oh, okay. Yes, I can hear you. Yes.
Good. Okay, so in parts 2 and 3, the objectives, part 2 and 3, just to give you a tour, if you will, of all the of different scenarios where Bayesian methodology is useful, certain applications that Fan and I have been working on over the years. And we're going to do these using some case studies. We are going to describe the data, the problem at hand, the distributional assumptions. Remember, we had that discussion last week about the appropriate distribution to approximate the data. We're going to talk about the priors, the choice, and we're going to show you some pictures of the priors that we select for a particular problem. We're going to show you, not only show you, we're going to walk you through the code. Mostly MCMC code. There's some BGLIMM in some applications. And then we're going to do some of the interpretation of the results and the Bayesian output. And hopefully you'll have questions for us, and we're going to try to take some questions halfway through and then at the end.
Yeah, the reason that we mostly will look at the PROC MCMC code is because a lot of the models are nonlinear and they require non-standard prior distributions. So they tend to be the type of model that BGLIMM cannot fit. But we'll explain as we go along on the details of the SAS code. Go ahead.
Exactly. And the other reason is, you know, through this you'll see the power and flexibility of PROC MCMC. You can pretty much handle a lot of different models and situations. We're going to talk about some of the technical details, not in depth. Here and there we'll mention some things to give you some background, but we'll have some references at the end that you can take a look. So we are going to do part 2. If you notice, we have 4 webinars, and the reason we have 4 is because we wanted to have enough time to go through all this. We don't want to rush through the material. So today, part 2, we may do it in this webinar. If we don't finish, then we'll continue next week, and then we'll probably start part 3 next week and then finish on the last webinar. But the idea in part 2 is we're going to talk about setting acceptance criteria, because that's an activity that a lot of us have to get involved in. And we're going to talk about different ways of evaluating comparability. And that is going to be done primarily with non-informative or diffuse priors. Then in part 3, that's where we're going to talk about using prior knowledge, historical information from other data sets, other molecules that we may have. And we're going to do it with some of the examples in part 2. And we're also going to introduce some new examples in part 3. Again, part 2 today, and part of next week will be looking at examples, case studies using non-informative or diffuse priors. And then after that, we'll get into the prior knowledge. Just a quick review of what we did last week. We talked about the Bayesian statistical inference. You saw a diagram like that for the frequentist one. And we mentioned that we have data, we have a quantity of interest that we want to either estimate or describe or predict. And then we have a likelihood. That is a probability distribution that we use to approximate our data. And they're all common to the frequentist approach too. The difference with the Bayesian approach, as we mentioned, is that we also have to deal with another probability distribution that is going to describe the prior information that we have. And that's the whole point of using Bayesian methods, that we can use that prior information. And that prior will be either diffuse or non-informative or informative. And then we have the Bayes rule, that is the one that we use to combine those two probability distributions, so we can end up with just one probability distribution. That's the posterior, and that's the one that combines the data knowledge, so to speak, plus the prior knowledge. And with that posterior distribution, that's the one we use for all the inferences. And we did talk about a little bit about how that's done, and we're going to get into the details today. Remember the Bayes rule. This is just a rule, a theorem that switches things around in the sense that we're looking at conditional probabilities. So if I want to look at the conditional probability of B given A, that's a function of the conditional probability of A given B times the probability of B, and this is the prior. We had that quote from Professor Efron, and then we highlighted suspicion because it is true that people sometimes see the use of Bayesian methods with a lot of skepticism and suspicion. Even the example that we show you from Professor Efron, if you remember, his friend, she was not that impressed with his answer of 1.5 or 50-50 odds of having identical versus fraternal. The whole point here is that the posterior beliefs are going to be proportional to our prior beliefs, and that's the main idea behind the Bayesian methods and using the Bayes theorem to that. Yes.
I do want to add a thing on the suspicion part of the thing. There is a Bayesian version of the central limit theorem where if you have more and more data does overcome any sort of a prior belief, prior information, that it's similar to central limit theorem, that the posterior distribution asymptotically does going to where you think that it should go to. And it's just when this suspicion part happens is when there are not a lot of data, then people tend to think that any prior distribution can have oversized impact on the posterior. So that's the point I want to add.
Yeah, and we'll show that theorem later on. We have that a little bit of the technical details. Hopefully we can cover that today. So we mentioned that in terms of estimation, we use the posterior mean, maybe the posterior mode. And in terms of intervals, we have two types of intervals. One is called the credible interval, which is an equal tail interval. And the other one was the HPD interval. And as you can define that as the smallest region with 95% probability, for example, that's the probability that we're looking at, or the most likely values. Tends to be narrower than the credible interval. But if you have a distribution that is bimodal, it can look a little funky. But we tend to use the HPD interval in calculations. But PROC MCMC will produce both. In terms of the prior, remember we talked about diffuse and non-informative, informative prior. Then Professor Gelman talks about weakly informative in the sense that people try to alleviate that suspicions in the sense of, well, if you're not too comfortable with the informative prior because may dominate the data and the calculations, we try to use less information that we have. But for me, that the weakly informative prior is not that appealing, especially in our industry, because we do have good information, good prior knowledge that can be used and that can be defended. And then that.
I just want to add.
Yes, go ahead.
I just want to add a bit on the non-informative prior discussion here. It is when Bayesian, last time we mentioned that Bayesians are fairly non-committed when they talk about non-informative prior, and there's a difficulty is in completely coding for ignorance. And a good example comes in the play is a just simple linear regression where you think, for example, people regress height and weight, and there is only one regression coefficient. So you know that if if we regress height and weight, the coefficient is probably positive, and the taller you are, the more weight you are, and the slope might be, say, within 0 and 200, however the scale that you're going to be. So if people are truly think about non-informative prior, a non-informative prior in that case would be equal likelihood on all values on the real axis. So let's just say they're from -2 billion to +2 billion, or however the value that the non-informative prior represents. It just means that I do not want to commit myself to any sort of possible value. I'm equally willing to consider all possible values. But from a distributional perspective, a priori, just before you see the data, your prior says you are 99.999% do not believe that a reasonable value is between 0 and 200. Okay, that by itself is information. It is a huge amount of information. That just means that you are a priori not going to believe what the data is going to show you. And that's a tricky part. Even though the name, you have a flat prior on a uniform prior on the real axis, you feel that is non-informative because you feel that you are assigning equal likelihood to all values, but that itself does translate to a very, very informative prior, in the sense of you putting so much probability mass in area that's outside of what you reasonably believe. And for that reason, you can see the difficulty of truly coming up with a non-informative prior. So that's what I want to add on this.
Yep. So, but hopefully we don't have to worry too much about that, because in the situations you're in, you probably have a lot of prior knowledge, historical data, knowledge from like products. You may be working on a mAb molecule, and you have history. Your company has been in business for many, many years, and you may have history from other molecules that relate to that. It's science and engineering based, and it's vetted by subject matter experts. And this is important when we're selecting these priors and this data to use as prior knowledge. We need that input from the scientists and the engineers that reflect what we call the disciplinary objectivity. We still, want to pursue objectivity, but there's always that tension between subjectivity and objectivity. It's very difficult to be completely objective. So what we mean here is this disciplinary objectivity, where there's a group of people that agree based on their science, their discipline, that these certain things provide information. And we'll show you some examples when we get into part 3. Not today, hopefully we'll start next week, when we bring in this prior knowledge into the Bayesian analysis. We talked about some of the advantages and disadvantages, and it's obvious. The whole point of Bayesian techniques is to use the prior information. And one of the most important things for me is that you can really interpret the results. You don't have an issue with the confidence interval meaning what it means, not that interpretation that people tend to have of a confidence interval in the frequentist approach. What most of the users think one thing of the confidence interval. They think that that confidence means that there's a probability of 95%, for example, that the true parameter will be in that interval. And that is not true within the frequentist framework, but it is true within the Bayesian approach, and that makes it very appealing. So if you have a credible interval, an HPD interval, you can say, yeah, there's a 95% chance that the true value of that parameter or that quantity of interest is in there. So that's appealing to the statistician and also to the users. We just had this discussion. Doesn't really tell you how to select a prior, but hopefully we'll give you some guidelines. We'll start to talk about this prior knowledge, this disciplinary objectivity, and things that we can do. Yeah. Fang just mentioned this.
Just to add on selecting the prior, and this is in a way that why these database informative prior is becoming more more prevalent in practice, because in essence of scientific discovery, we are using information that built from the past in the inference whether we like it or not, in for data that we are seeing in the future. And so the informative approach, especially based on the data, based on the past experience, based on the expert knowledge, becomes a formative way of constructing an opinion that people, even it's informative, but people have the tendency to agree upon and to rely on. So that's
Yep.
like the tricky part is that you have to have an opinion. That's, you know, as we say a lot of time, it gets a bit tricky.
Yeah. And we do it. I mean, I think the Bayesian framework works very well with the way science and engineering works. For those of you who are familiar with the book Statistics for Experimenters by Box, Hunter and Hunter, they have a very nice diagram of the interplay between the theory and practice, between induction and deduction. You have a theory, you generate some data, you do some statistical analysis, and then you make some inferences, and then you go back to the theory and up and down in that cycle. And here, you know, this Bayesian framework fits that perfectly. I mean, we never work in an isolated case. We always have some historical information, some theories, some ideas of what things are going to be.
Hey, Jose, we have a quick question. I'm monitoring the, I think it's a quick question. And the question is, do regulators accept sensitivity analysis as results coming from different priors? I do think that there is almost an obligation to do a sensitivity analysis in presenting your work, just not to show that you get a different prior, you get different posterior, which we know that is a fact, because if you have a different 1,000 prior, you will get a different 1,000 posterior by the simple application of the Bayes theorem. The likelihood times different prior, you get a different posterior. So the purpose of sensitivity analysis typically is to demonstrate that you are not trying to playing a game and using prior that's favorable to your hypothesis in inferencing the output. And I think that's the objective, and that typically is being asked to.
And one of the things I'm going to add, we're not there in CMC. I mentioned this last week. In the clinical side of things, the FDA does accept some submissions and Bayesian methods. In CMC, we're not there yet. Our hope is to change that suspicion perspective that they may have. And one of the reasons we made these webinars open to the public is with the hope that they will join us so they can see the applications and have these discussions. And along with the sensitivity analysis, another thing is that we need to be very transparent in terms of how the prior was selected, the reasons, the historical information that we're using. And that's what I talked about, that disciplinary objectivity, and that is vetted by the SMEs. The SMEs, you know, there's some science and engineering behind it as to the choices of the data and the prior knowledge and the prior. So and the sensitivity analysis plays a role. Yeah.
I'm just adding another comment from Brian. We are always concerned whether or not FDA or any other agency will accept a Bayesian analysis. Yeah, that is true. They have not come out formally on how to do that, as we know of. And I have to say that partially, I've gone to the discussion with them. Partially is because their prior would inherently be very different prior than what we see, because if you submit a thing, your prior is that it's going to work, or you can be somewhat skeptical that it's not going to work, but mostly that the prior reflects the belief that it's going to work. But from a FDA perspective, most of the submission probably don't work that well, so their prior is much more skeptical. And how do you bridge the two gaps is one of the big issues I think they need to give it. So. Yep.
And we'll be talking about some ideas to do that, and I think this will take some common effort. You know, so I'm hoping that, you know, the IQ, I mean, at least the statistical leadership group, since it has members from all different companies, that we can work with them and suggest some guidelines and stuff. There were some nice discussions at the nonclinical biostatistics conference that happened a month ago. There was a panel discussion on this. So things are moving. I mean, we're not there yet, but I'm very hopeful because there's a lot of interest now. Even internally, I don't know in the companies you work for, but even internally, things are changing a little bit and people are starting to warm up to the Bayesian methods. And again, this is one of the reasons that Fang and I are doing this, so people get exposed to all the different ways of using these techniques. So let's keep going so we can show you some of the examples.
We see there are a couple more questions, but let's wait till a later break point discussion.
Let's wait a little longer. Top of the hour. So it's a high computational cost depending on the problem, but so it's within reason. And we mentioned this last week as part of being able to reproduce results and all that. It's important to keep the random seed that you use for this. If you use PROC MCMC, for example, without specifying a seed, it will take the seed from the clock of the computer, and every time will be different. So it's a good practice to save the random seed that you use and provide that. Then at least I will guarantee the same results. Okay. So why Bayesian statistics? We show you that before is because we can incorporate prior knowledge. That is the base rule there. So we have the data that has the likelihood, the distribution, and some type of statistical model that we want to use for inferences. Then we have some prior distribution here. We're showing you a flat prior, that the one that Fan was talking about. We're non-committal, any value there will work. And then we combine the data here with the prior and generate a posterior distribution. And then we use this distribution to perform all the inferences. And you'll see how we do that in different scenarios. But now the difference again is we're going to use this posterior distribution for the inferences that we're going to use. And again, posterior beliefs proportional to prior beliefs. So let's look at some of the case studies, and we're going to start, as I mentioned, with setting acceptance criteria. And for that, one of the techniques that people use are tolerance bounds or tolerance intervals. So what is a tolerance bound? Let's review this quickly so we're all on the same wavelength, so to speak, so we have the same definition. So the idea is we want to find a bound that captures a certain percentage of the population, because we want to make a claim about the population. Remember, we talk about making claims. A lot of the work we do is to support the claims that scientists, engineers, and people in regulatory want to make, about a particular product. So sometimes we want to make a claim about the population. If I get some data and find a bound, my claim is in the future, we expect certain percent of the population to be either above or below the bound or between an interval. So for example, that's what we call the coverage. So if we use 99%, what we're saying is that the probability that a future observation will be less than that upper bound is equal to 0.99, or I can say the same thing as 99% of the distribution of X is less or equal to that upper bound. And below that, there is your normal distribution, and that shaded area is the area below 2.35 there, and that is a quantile that covers 99%. Below that number, okay, for a normal 0, 1, you have 99% of the population, or the probability of that being there is 0.99. However, that assumes that we know the mean and the standard deviation exactly, okay? And that sometimes people tend to forget. We all teach people and we all use the quick rules of 68% between plus or minus 1 sigma, about 95% between plus or minus 2 sigma, and about 99% of pretty much all the population between plus or minus 3. And that works, some quick calculations. But in reality, that's only true if you know the parameters of the distribution, but we don't. And because we don't, we have to estimate that bound with some confidence, and that's what the stats come in, and that's all the theory behind tolerance intervals and tolerance bounds. But if you look at just a bound, you can think of a tolerance bound. The one-sided tolerance bound is just essentially a confidence limit on the p quantile, okay? So if you look at a quantile of a distribution like that number there, the 2.326, That's a quantile that covers to the left 99% of the population, 99% of the area. Okay. If we want to add some of the noise coming from the data and coming from the sample size and all that, we cannot use that. We have to use a number that is a little higher than that. So we put a 95% confidence, for example, bound on that quantile, and that is the tolerance limit, the tolerance bound. And we're going to use this definition when we calculate the Bayesian tolerance bounds, because what we're going to generate is a posterior distribution, yes, for the quantiles. So in the Bayesian analysis of setting limits, we're going to generate the posterior distribution for the quantiles, and then we're going to look at the distribution, and we're going to grab the corresponding percentile of that distribution to the left or to the right, depending if we want a lower bound or an upper bound. Okay? And you'll see how that's done. But that's the main idea. Okay? So these acceptance criteria or tolerance bounds are commonly used to set, for example, process controls, to assess limits. For example, if we're looking at air levels, the limit right now is about 0.15 micrograms per meter. So you may generate a tolerance bound, and as long as your tolerance bound is less than 0.15, then we can say that, yes, we're meeting that. If we're above that, then we have an issue. We can use them to set a specification. Sometimes people take the bounds as a specification, which is not truly recommended. What I suggest is that those are starting points for the SME, for the subject matter expert, to define or start working on the specifications. But all these limits are based on a distribution that adequately describes the data. And I mentioned this before, we mentioned this last week, that we tend to use a normal distribution for everything. And even software by default uses a normal distribution. So if you go to SAS or jump to compute a tolerance limit and you hit return, then you're signing on the dotted line that the distribution you're using is the normal. And you'll see that in some cases that is not the most appropriate thing to use. And that's another reason why I like the Bayesian framework. One of my pet peeves, I mentioned this before, is not using the distribution that is appropriate to the data that we have. Okay. So if you're a frequentist, they're at exact tolerance bounds and tolerance intervals based on the non-central T, and you can get those out of PROC capability or jump, for example. If you have a data that can be approximated by a log normal distribution, you can take the log of that data, and because the log of the log normal is normal, then you can use all the techniques for the normal, and you can transform back, and those intervals are exact. If you have a gamma data that can be approximated by a gamma distribution, amazingly enough, the cubic root transformation does a good job, has good coverage. For the Poisson and the binomial, Krishnamurti have given some closed form approximations for them. And Krishnamurti is one of those experts in the area of tolerance intervals. He has a book with Matthew called Statistical Tolerance Regions. I highly recommend that if you have to do these things from the frequentist point of view. But what about the rest? Okay, these are just some cases. What about if you have yield data or viability data or size exclusion data, some impurities? That data is bounded between 0 and 1. So the normal distribution is not a good approximation for that. Maybe if you're in the center of the range, it may work. But if you're working with viability, for example, your viability, if you have a very good process, is normally around 0.98, 0.99, close to 1, like that one in the picture. So you can see that a normal distribution will not approximate that data well. Also, a normal distribution is defined in the real line from -infinity to infinity. And what happens, and we see this a lot, is people may use a normal distribution for this type of data, and you may end up with a limit that is greater than 1, which makes no sense from the science point of view. Or if you're on the left, on the other end, if you're here, you may end up with limits that are negative. And then what people do is, oh, okay, well, it's negative. We'll just truncate it and set it to 0, which is not a good practice since we have the techniques to deal with that. What if you have count data, so visible particles? No, they can be approximated by a Poisson, and if you have over dispersion, it's the negative binomial. How do you deal with that? Yes, Krishnamurti has an approximation for the Poisson. There's nothing like that, but there's something like that for the negative binomial. We'll talk about that, but it's not. They're all approximations. What if you deal with positive quantities like extrusion or strength or break loose or volume? They're all positive quantities. Again, if you're using a normal distribution, you may end up with a negative tail that would give you negative prediction or negative bound. So if you have the type of data, why don't you use a distribution that is defined in the positive side of things, you know, from 0 to infinity, like the Weibull, the log logistic, the Frechet, the log normal. And the people in reliability engineering, they understand this clearly. I mentioned this before. They work with positive quantities all the time. So there's not such a thing as a negative force. So they tend to use this. And the Weibull distribution was developed to deal with these type of properties. Okay? So I have to tell you that a lot of your data cannot be approximated well by a normal distribution. You all hopefully know this. Okay? But sometimes it's a little frustrating because what we're going to do if we're using a log logistic, how we're going to get a tolerance bound if I want to approximate that for a log logistic. We're going to show you how to do that using the Bayesian techniques. So how do we do this in the Bayesian framework? As I mentioned, we're going to generate samples from the posterior density. Whatever distribution that we define for the data, along with the priors that we define for the parameters of that likelihood, then we generate a posterior distribution for those parameters. And one thing that we mentioned, and Fang spent some time last week talking about this, is that once you have these posterior distributions, you can plug them in any function of the parameters. So if we have the formula for the quantile, then we can plug in the mean, the posterior mean and the posterior standard deviation, for example, and calculate the posterior distribution for the quantile. If you want to create a weird function, which is this quantile plus the square root of the other quantile divided by 3,000, you know, you can also get a posterior distribution for that, and that is the flexibility of this approach. So once you set up the problem, the priors, the likelihood, and get the posterior, then you can pretty much generate inferences for quantities of interest. So what we're going to do is generate the posterior for that, and then we're going to grab the quantile function for the likelihood and generate the quantiles for that, the posterior distribution of the quantile. And then once we have that, you know, we'll base the inferences there. So, and we'll talk about more about Wolfinger in
one thing I want to add.
Go ahead.
With these functions of parameter. So another advantage of Bayesian is that, specifically to PROC MCMC, not necessarily to Bayesian, but to PROC MCMC. Sorry, not to PROC MCMC, but to MCMC simulation-based estimation methods in general, is that the samples that the Monte Carlo samples that you get from a posterior gets you the marginal distribution directly, and which is very important. The marginal distribution is what you want to infer on while accounting uncertainties from all other parameters. So you can have a model with many different parameters, and the marginal distribution you get on the parameter of interest account for all uncertainties from any other parameters. In other words, the functions of these parameters, which will quantify the scientific interest, were already accounted for uncertainties in the model. And that's not when you come to think about it, is computationally is a very difficult thing to do, because they have this potentially have a high dimensional correlation and nonlinear quantity. But if you do MCMC, you get the marginals of the parameters in marginals, and you get the marginal estimation of the functional parameter by counting one.
And that's key, what you just said, Fang, about the different sources of variation, so to speak. All these uncertainties are taken into account, and you'll see later on some examples of that and how this approach is powerful, because you can as long as you set up the model, you can bring all the sources of variation above and beyond what you can do with the frequentist approach. We're going to be talking a little more about
just a
the
clarification
Wolfinger paper.
Now, do we need to consider a prior pre-using posterior? I'm actually not quite sure what that means then. And then Brian has a question, so that in other words, we do not need to worry about multiplicity.
Well, we'll talk about that. We'll talk about that.
Sure. I'm not sure, Brian.
Yeah, we'll talk about that. We'll talk about that. Yeah. Right now, it's just will be just one thing at a time. But there are situations that we may need to talk about that. You know. Yeah. Yes. And hopefully, the question about the prior, once you see the examples, you'll see how this works, and then that may help. Okay. So the approach, again, we're going to specify a likelihood function, a distribution for the data, and we're not bounded by the normal. We can use pretty much any distribution that is appropriate to the data at hand, to the data generating mechanism. Once we have that, then we're going to specify priors, either diffuse or informative, about the parameters of that likelihood. And it can get a little more complex. You can have some hierarchical models. And by the way, a hierarchical model in the Bayesian framework is variance component models. It's a way of thinking from the frequentist point of view. So Bayesians, when they look at variance components in different levels and all that, they think of hierarchical models. And I know Fang will jump and correct me right away. So once we have the priors, then we generate samples from the posterior, and this is using MCMC. And we'll talk a little bit about MCMC later on, give you a little insight into the technical details. Once we have that, as we just discussed, Fang told us about the marginal posterior, we use that to generate the peak quantile of interest. Remember, we want to find a quantile that covers certain percentage of the population. So each MCMC sample, we generate a whole bunch of samples when we run PROC MCMC, 1,000, 2,000, 10,000. Each sample will generate a quantile, and then we'll have 10,000 quantiles there. And those 10,000 quantiles will give us the distributions of the quantiles. And then from that distribution, we're going to select the appropriate percentile, you know, for that. If we want a 95% bound in the quantile, we'll select the 95th percentile. If we want a lower bound, we'll select the 5th percentile to keep 95% to the right. And these ideas were first presented back in 1998. You can believe that is, you know, so long ago. If you know Ross Wolfinger, he worked for SAS, and he was the main developer of PROC Mix and the GLIMM Mix macro. Some of you who have been using SAS for a long time, you'll remember the GLIMM Mix macro before PROC Mix came along. And back in 1998, he had this very nice paper on tolerance intervals, and we're going to talk a lot about the paper because we're going to follow some of his techniques. Then Krishnamurthy and Matthew, that's the book I mentioned, Statistical Tolerance Decisions in 2009. Meeker and Han, that's a great book on statistical intervals. I use it throughout my career. There's a new edition that came out in 2017, and Professor Escobar is now one of the authors there. They included Bayesian techniques there. And then myself and Randy Tobias gave a presentation at the Quality and Productivity Research Conference on 2018 on calculating tolerance bounds using Bayesian techniques. And some of the examples that we're going to present here come from there. So those are some of the references, and you'll see it at the end. Okay? So to estimate the bounds, you got to specify the likelihood function. And there's a little bit of SAS code there. So we're saying the model for Y, in this case, is a normal. Okay? And then you see we're going to draw posterior samples using PROC MCMC. And you notice we compute in the quantile. But notice what happens. The quantile, we say, okay, we're going to compute a normal quantile. And the quantile is a function within SAS. And for the quantile, we need the coverage, that is the 90% or 99%, Okay, that's the P. And then these mu and variance are the mu and variance in here. And then we also have a prior on the mu and variance. So it's very easy, very clean within PROC MCMC. You define the likelihood, you define priors for the parameters, the mean and the variance, and then you pass those parameters literally just like that to the function. And this will calculate the quantile of interest, either lower or upper, and then you'll have the posterior distribution of that. And
Yeah,
kind of works for any distribution, quote unquote.
right. Well, the reason that when we put quote unquote of any distribution is that because of this quantile function, technically in SAS only supports a number of standard distribution. And if you are working with a likelihood that has not a standard distribution, which means that you will need to use a general function in SAS to define. And then now this becomes almost a censored information. You essentially censor information, which we don't really do, but it's a predictive distribution in the sense of condition on the posterior sample of mu and the variance, which you know have many thousands, because they're coming from distribution. You would want to generate a distribution of the response variable. And that's a predictive distribution. And as a predictive distribution give you the density estimation, which then you can compute in a quantile according to this non-standard distribution. So it's doable, but it's not as clean as if you knew a priori how have the quantile function that's available to you.
Yeah. But having said that, I mean the list of the available distributions is quite extensive. So I mean, it has to be a very special case, and you'll see this. We're going to show you the use of many different distributions that are the ones that we encounter most of the time in practice. But as Fan said, you know, if you have a very unique distribution, you can handle that. It will take a little more work. Okay? So we're going to show you some examples, various situations. We're going to start with normal data. Then we're going to look at some count data, viability, that's data between 0 and 1. We're going to look at limit of detection data. This is data that we have in CMC, but in my experience, sometimes or a lot of times it's not treated right in the sense that LOD data is sensor data. So we have to treat it accordingly. I keep mentioning reliability engineering. Reliability engineering has a lot of methodologies for dealing with sensor data, any type of sensoring. But my experience is that when we encounter LOD data, we either set those values to the LOD, which tends to bias the data, or we discard the LOD data, discarding good information. So there's no issue here within the Bayesian framework of dealing with that, and it's pretty flexible. And then we're going to set up some tolerance bounds when you have a model. So far, you know, when we do these, oh, it's some data set and we compute a bound if you're in the frequentist point of view. But what if you have a variance component model? What if you have samples that are batch and within batch, and you have a structure in your data? How are you going to compute a tolerance bound in that situation? So we're going to show you that this framework is very flexible and can handle pretty much any model that you can write. So it's a little bit about non-informative priors, just to show you, this is from Professor BGLIMM, and the different ideas, is a lot of stuff in terms of using non-informative priors, this idea of being non-committal, but as Fang said, it's very hard to have no information whatsoever. You always have some type of information, and a lot of the work has been done too, is to generate priors that are going to give me some type of agreement with the classical estimators. And just want to point out here, you notice that there is a book by Professor Box and Tiao back in '73, and it's a Bayesian book. So that's what I mentioned last week, that in the old days, you know, the frequentists were not afraid of using Bayesian techniques, and they use both. And one example is Professor Box, that you all know well, has developed a lot of the techniques that we use in industry. And I always joke that I'm happy that we don't have to pay royalties, you know, every time you use a CCD or any type of time series analysis. Anyway, he wrote a book on Bayesian techniques.
There is a school of thoughts of constructing prior using information from the data. invariant Jeffreys is one of them, and there's also extension by which things such as a unit information prior, that people feel they would feel comfortable if the prior contains information represented by a single data point. So it is some information, but not overwhelming amount of information, especially when the data gets to be large. So there's variations of them along that type of interpretation of non-informativeness in this. And for a long period, I mean, I think nowadays still to some extent is that people would like to see a match between a Bayesian analysis and a frequentist confidence interval in the matching. You sort of almost get the best of two worlds in the sense of you can do a Bayesian analysis and you have the HPD, or you have the credible sets, and if it matches with a confidence interval, then you get coverage probabilities, sort of a bypass product of it. It does get tricky because, philosophically, if you truly want to say that your analysis wants to agree with the frequentist approach, then maybe you should just use confidence interval-based analysis. And then the branch of informative Bayesian analysis just to think that we should use a prior which mostly represent our information, and the consequence of which is a posterior. So.
Yeah. And if you haven't done a lot of Bayesian analysis, you're going to get into it. Don't be surprised. It's a lot of work that's been done in all these areas. And the people talk about diffuse priors, non-informative prior, weakly informative prior, reference prior, maximal information density prior. So a lot of work has been done in this. So we're just going to show you a few things, but it's out there. So but it's been around for a while. People trying to match.
Quick clarification question: can we derive confidence interval for sums of variance components in intermediate precision? I think so, but maybe
yeah, we can. We're not going to show it, but we can. You will see some of the examples, and again, any function of parameters that you can think of, you can write it in the code and generate the posterior distribution of that quantity. So that's again one of the beauties of this. So as long as you have the variance components will be part of your analysis. Then functions of those variance components will get a posterior distribution, and then you can make inferences on that. And you'll see a little bit of that because we'll have an example on variance components that comes from the Wolfinger's paper. Okay, so let's start. We're going to start with simulated normal 0, 1. Why? Because we know the normal, even though I bash the normal a lot. I'm going to start with that. This is 100 observations from a 0, 1 normal, and I want a 95% confidence, 99.865 tolerant bound. And some of you may be thinking, wow, that's an odd number, Jose, 99.865. But some of you may realize that the 99.865 is a 3 sigma equivalent bound. So if you have an upper bound for a normal distribution, then 99.65% of the distribution will be below that number. Or if you have a lower bound, will be above that. So that's a common coverage that we use in industry to use, as I say, 3 sigma equivalent bound. So, and we know that number, if we knew the mean and standard deviation of the distribution, that number is 3. But again, that number is not going to be exactly 3 because there's a sample size and there's a noise in the data. Luckily for the frequentist, there's an exact lower bound calculation derived based on the non-central t. For the Bayesian, we're going to use diffuse priors on the mean and the variance. And as we mentioned in the Bayesian approach, we're going to generate posterior distributions. Once we had the posterior distributions of the quantile, okay, then if we want the lower bound, we're going to grab the 5th percentile of the posterior distribution of the 0.135% quantile, and that's 100 minus 99.865. Again, we want that because we want the lower end. So let me show you what happens before we get into the code. Gonna highlight the numbers. The top row is the frequentist, the bottom row is the Bayesian. These are very, very similar results. And we are using the word comfort on purpose because we're trying to dispel some of that suspicion. So this is, Fan just was talking about this, about matching things. In some cases, you can match the results. So in this case, if you have normal data and if you use these diffuse priors and you want to generate a 95%, 99.865 coverage lower bound, you get essentially the same number. Okay. Under the exact frequentist approach, the number is minus 3.22. Under the Bayesian approach, it's minus 3.22. And notice that this number is less than minus 3.22. And that's because, that takes into account the sample size and the noise in the data and all that. So we're just going to start with the results, and then we're going to show you how we get those numbers.
Yeah, one really should not be surprised by here because even in a frequentist likelihood-based estimation, you're maximizing your likelihood function, which is a normal function, and you're maximizing with respect to mu and the sigma square. It is equivalent, since everything is flat, it means there's inherently implied a flat portion on mu and the sigma square in the measure, in the big measure, that they are flat, and so you essentially get identical answer in the MLE as you would get from a posterior mode. But the posterior, since everything normal looking, including the nicely behaved posterior distribution of mu and sigma square, that the posterior mean estimates is essentially very similar. They integrate out of with respect to all the inserting the mu and sigma square, you pretty much recover the entire thing. So that's why.
And this is the opposite of what we're saying, that you sometimes, if you use informative priors, they may tend to dominate the data. In some cases, with non-informative priors, they do not dominate the data. But since we're basing the inference on the posterior distribution, then we have all the philosophical interpretation of these quantities. So how do we do this? Well, we're going to put a diffuse prior on mu, and we're going to use a normal with a standard deviation of 100, and that's what it looks like. So it's centered around 0 and it's flat. Can be any number there. And for the variance, we're going to use a gamma here with the shape and inverse scale. It has a mean of 1 and a very large variance. And one of the things that we're going to be talking about is this parameterization, and it's important how you specify these parameters. In fact, you may want to say a little more about I scale versus scale and all that.
Yeah, that's one thing I want to say, but I want to add that I want to explain why people consider this to be a diffuse prior on sigma square, even though it is very peaky, close to the tail. This distribution it peaks at 0. The red bar coming down 0 is artifact of the simulation of a density estimation, but the distribution is like exponentially decay tail to the right. And you look at it, you say it doesn't look like non-informative at all. And why is that we call it non-informative? This is because this distribution, the shape of it, mimically closely to this thing called Jeffreys prior, which is 1 over sigma square. And why do people think Jeffreys prior is non-informative in that sense? Is because Jeffreys prior 1 over sigma square as a prior distribution is equivalent to be uniform on the log scale. Okay, so it's a uniform prior on the log scale, but when you transform back to sigma square, it has this shape to it. Jeffreys prior at the same time is considered to be invariant to transformation. So more or less, it's non-informative in one dimension. It's considered to be somewhat non-informative in a different dimension as well. And even though this has a weird shape, that's why people still tend to associate this prior to be non-informative because of the shape similarity. But I can see that you already are being skeptical. I mean, looking at the shape of it, you can't say it's not informative. It just shows you how difficult it is to truly get a non-informative in the sense that everyone agree upon. So that's a bit that I want to add. Yep.
But having said that, Fang, there is some agreement among the experts, for example, that the gamma is a decent prior, to use
Yeah,
one
it's a
word,
decent prior. It's decent prior.
For variance components. So in a lot of work that you may do with variance components, you may want to use a gamma distribution. And this is what we're talking about in terms of, in the future, so generating some guidelines and things. So for variance components, you may use a gamma. Professor GBGLIMM has some recommendations as to other distributions like a half Cauchy or half T for variance components. But in our experience, at least the gamma has worked well in some problems. Okay. So again, the idea here is to give you
just let me add one more sentence. And then people say, if Jeffreys prior is considered to be non-informative, why don't we just use Jeffreys prior in many cases? Invariance component, unfortunately, the Jeffreys prior lead to improper posterior. So you can't just, it's an improper prior to begin with because it doesn't integrate to one. It doesn't have finite integral. But in cases like a variance component, it's the Jeffreys prior leads to improper posterior, so we can't use it. So, but this is a proper prior. That's it.
Yes, and this is a point we haven't talked about, but I'm glad that he's bringing it up. This having a proper posterior is key. And you'll see some cases where we may have an improper prior, but the posterior is proper. So you have those things there too. So it's not as straightforward, but hopefully,
in general, this is a user responsibility. Like if you're gonna do the analysis, if you want to commit yourself to be a non-proper prior, it's your responsibility to show that the posterior is proper. Most people don't want to bother with it, especially in cases like Jeffreys prior, because it's unclear. In some cases, it's being worked out. That's fine. Generalized linear model, it's being proven. But when you are in doubt, you should stay with proper prior.
A proper
prior just means that's a proper distribution and integrated finite integral.
Yeah. And this is part of the transparency of how we select the priors and why. And I'm a visual person, I like pictures, so this gives you a sense of what the priors are. So we're non-committal knowledge about the mu. You can see that this distribution, you can see it has a standard deviation of 100. It's pretty wide. Okay, so now that's the prior information, and this is the code, the MCMC code to run these calculations.
Yeah, the MCMC code in this case is very straightforward in the sense of you essentially just have a normal likelihood with unknown mu and sigma square. And if we are unknown about mu and unknown about sigma square, in frequentist approach, you just maximizing with respect to the likelihood function, you get mu and a sigma square. We essentially doing the same thing, but we just need to express two priors for mu and sigma square, and that's what the prior on, we know the likelihood function parameters of mu and sigma square, and then you have the prior, and each has a normal and a gamma, and then your likelihood, just to say what the likelihood is, it's just a very simple
before you go, Fang, before you go on, you mentioned this last week, but it's important to notice you have to tell MCMC what you're using. Here I use variance.
Right.
Yes, standard deviation was 100. So you can put SD equal. Yeah, you can put SD equals 100, or you can put variance equals 10,000.
So
if you put 100 here, yeah.
In prior specific distributional specification in MCMC require, there's no default way of to say what my values are, and you need to sort of put or you need to mean what you want in terms of parameterizing a prior distribution, variance, standard deviation, precision, or normal, inverse gamma, and inverse scale or scale for a gamma or inverse gamma. It can get very confusing at times because you kind of don't know what to visualize things in that way, but that's why using the procedure as a way to simulate from the data and then visualizing it from the prior sometimes is a very good way of understanding the prior distribution that you are seeing.
That's
So,
right.
so
And that's why we had the picture.
Yeah.
So again, these are the little tricks, the little tricks that we as practitioners need to remember. And now we're telling you that. So go on. So here is
and then you have the likelihood, and now just the three parts, the prior and the model jointly define the posterior, and the PROC MCMC will sample from the posterior distribution of mu and sigma square. And then now it comes to the next step. And then the next step is you want to giving many samples of mu and sigma square. And the reason why many samples, because they are coming from the joint posterior distribution of mu and sigma. And for each pair, you want to compute the quantile at 1 minus 99865, and the 0.00 is 0.135%. And so for every pair of mu and sigma, you get a value of QL, and then you get tens of thousands of QLs, and then they form a posterior distribution of that quantiles, by which then you can estimate what you need to estimate. So
exactly, and that's the beauty of it. You can see that that's all within the PROC MCMC code. So we're defining the priors, as Fang said, the model, MCMC will generate the posteriors, and then we're computing standard deviation just to show you a simple calculation. And then SAS as a quantile function where you can specify the distribution, and then you pass the parameters. Here will be the colors, and the mu and the sigma are these mu and sigma.
And this is a big thing about quantile itself is a data step function. And the data step function does require the specification on the standard deviation, not on the variance. So it's a bit somewhat of inconsistency, because quantile function has come out many years ago, and then you've just set to be standard deviation alone. And that's why you're required to do this transformation from the variance S2 to standard deviation of sigma. So that's just why there's an extra step of what you calculation.
And notice here, this is key to, there's this statement called monitor. These are the parameters that you want to monitor. You may have intermediate parameters that you don't care about, but whatever you put in the monitor, you'll see the posterior samples in the data set. And these outposts is the data set that contains the posterior samples. So I'm calling it normal POST. So these data set will contain a whole bunch of information plus posterior samples for mu, the variance, the standard deviation, and that lower quantile that we calculate.
Yeah, and in this simulation is very fast. Since I don't know, but it just a question of how long it takes was 500,000 simulation, but it's very fast.
It's very fast. It is.
Yeah, in this, and of course in the when the model gets more complicated, when the data sets get to be larger, you do nonlinear, you do random effects model, it will take longer. Yes, that's the question.
Yeah, and we'll talk about that. I mean, there's some examples in part 3 that are like that, but these type of things run relatively fast. Okay, so this is the output for PROC MCMC. You here have the parameter estimates, so to speak.
The parameter estimates for the mean, the standard deviation, the percentile by default, and then it also computes two posterior intervals. Equal tail just means, 50%, 5% and 5% on two tail, and
that's a credible interval.
Yeah, in general they are called credible interval, but mostly when people say credible interval, they sometimes refer to the equal tail interval, and then the HPD interval is for the smallest interval that's most concentrated, and you can ask the procedure to change different alpha level from 90% versus 95% and so on. But
yeah, so by default
as the output, the default is 5%, I think.
Yeah. Here I change it to 90%, so you can see it.
And then this is the trace plot. That's we don't really need to see that, but we just want to run a very large chain to show you that some of the output of the density, and that's for the two model parameter mu and the sigma square. Yep.
So this is a posterior distribution, the posterior density for mu, and this is the posterior density for the variance. And no surprise there, posterior density for the mu looks like a normal, and the posterior density for the standard, for the variance, looks like a gamma chi-square type distribution.
Yeah, because the sigma, even for sigma square, it is normal enough. That doesn't quite happen all the time. Sometimes sigma square just tend to be right heavy, but in this particular case, both of the posterior distribution look somewhat like normal. That means the posterior mean estimates are very, very close to the MLE, and that explains why the answers are so close to the frequentist approach. And then then a way to summarize the visual display is the effective sample size, and effective sample size is close to 50,000, and that's very, very good, an indication of efficiency in sampling. And a related concept of effective sample size is a Monte Carlo standard error, which showed on the second page of it. So there are two variabilities. The posterior estimates that you see is subject to two sources of variation. One is the posterior standard deviation itself, because that's what we want to quantify. That's due to the data. That due to how much normal data one gets, and that's a sampling variation, which we want to quantify. And the second is this thing called Monte Carlo standard error. That's a variability that's due to just running simulation, running Markov chain many times. If you run it again, you're going to get a different thing. And so you want to get a handle on how much variability coming from which aspect of it, and that's a ratio between Monte Carlo standard error and posterior standard deviation. And you want to be in at least a factor of smaller, just to make sure that your simulation variability doesn't contribute too much on the posterior estimation. And that's what this table is for.
Yeah, so you want those numbers to be small, and the reason we're showing this, remember last week that we had those questions about thinning, and Fan gave a good explanation about thinning. We're going to talk about thinning again later on, and one of the things that Fan said, and I learned that from him, is the number to look at is effective sample size. So this is a key number when you're evaluating the results. Yeah.
Yeah, and in this particular case, we're being very conservative. That's why we run very large chain. I think that in most practical purposes, in the low thousands is sufficient.
Yeah.
So
and we'll see that in some of the examples. This is just because it's all textbook type data, just to show you how things look like in this ideal world. But the key point here again is to look at some of these plots, and the trace plots, and then to look at the effective sample size. I remember, Frank, you mentioned this number you wanted to be at least 1,000, no?
Yeah. In thousands. I mean, the reason that they say thousands is you can try this out yourself. That's what they teach, is that if you want to do a random number generator to approximate a distribution like ran normal or R norm in R, 1,000 sample size gets you a pretty good idea to what the distribution you want to approximate. We're talking about in general like the normal distribution and whatnot, and that is equivalent concept of how frequently that these samples have explored different aspects of the distribution. And if you explore it sufficiently by proportion, 1,000 is good enough to get you very good estimates of it. Which SAS version is this? I think what did you use? 15 point, what SAS version do you have? 15.1? Just question which SAS.
It's 9.4 TS1 M6.
Okay.
See,
M6 is 15.1.
We don't remember the stat versions, because you have the stats version, plus now you have a stat 14.3, stat 15.1.
Right.
So this is 9.4 TS1 M6.
Yeah, this version of this capability of MCMC has been around for about 10 years, so it should be good. We do not seem to get the Monte Carlo standard error. The Monte Carlo standard error just is essentially to estimate how much estimated variability is contributed to simulation. That's the concept of that. And did you not specify that option in the code? Well, we didn't show the code. We just the code that we showed didn't have a diagnostics equal to all option, but when we run the example, we run it. We don't want the code to overwhelm the display on top, but to specify an output of a specific type of diagnostics. You just say diagnostic equal to all, and it produces all of it. And we didn't display it. Sorry about this inconsistency.
Yeah, no, but I'm glad that people are paying attention. So we just want to show you this is the first example. We're just showing you the basics of the code, so you get an idea where the numbers are coming from. The last thing, this is the diagnostic for the quantile. Remember, we put the quantile function within the MCMC code, the PROC MCMC code, and this is a posterior distribution for that quantile. Remember, that quantiles for 99.865, the lower bound should be around -3, because that's what theory tells you, and that distribution is around there. I'm going to enlarge that. So that is the posterior distribution of the quantiles, okay? And then what we're grabbing is the 5th percentile of that distribution. Remember, a tolerance bound is a confidence bound on a given quantile. That's the definition, and that's what we're using to calculate these things. So here we're just grabbing the 5th percentile, which is this line here, and that's a 3.225. So again, we take into account the uncertainties of the data, the priors, and the variability in the data, and that gives you that number. In theory, if we knew the numbers exactly, as we said several times already, that number should be -3. But it's a little lower than that. And as if those of you familiar with tolerance bounds know that that's a function of that K factor in the tolerance bound calculation. So that's an example for the normal distribution. You see how simple it is, relatively simple it is to code and to generate that, and you got similar results. So let's look at something more interesting.
Wait,
let's see. Let's take some questions.
12:17. So why don't we just answer some of the questions that we said we were going to answer,
let's do
and
that.
then so people can take a quick break, and let's both look at the let me read the questions. Sorry. Let's see. We are always concerned whether or not the FDA anything. The question then becomes to select appropriate pessimistic prior for sensitive analysis. Yes, Brian, that's correct. That can
you repeat the question?
Oh, the question is, when we're talking about sensitivity analysis and the FDA agency will accept the Bayesian analysis, Brian said the question, made a comment, the question then becomes how to select an appropriate pessimistic prior for sensitivity analysis. Yes, they do have, they call skeptical prior and more pessimistic prior. So that's in the sense of they truly do not believe something is going to work. And they are asking, yes, they are. That's correct. Will we move into a situation where certain priors will be accepted for certain problems? I don't want to speculate, but I think it's probably going to be reasonably inevitable that people will accept a class of acceptable prior, like the prior on the variance component, and maybe 5-6 of them, and then the prior on the regression coefficients, whether people is allowed to use information, historical information, whether use data from the control group to form opinions in the prior, and such, either data driven or historical data driven, or non-informative in the sense of acceptable non-informative. I mean, that's my speculation.
Yes, and that's not only that. That also my goal. I hope I mentioned this a while back, that I hope as companies, member companies in the IQ, for example, we can work together with the agencies to generate something like that. And in this example, we're going to mention a document that is out there, not sanctioned by the agency, but that's the idea, to have, as Fan just said, a class of priors for a particular problem. If you're dealing with count data. These are some of the priors that you use. You dealing with variance component. These are some of the priors that you can use. Then that way, people, there will be some quote unquote standardization of things.
Given Bayesian probability definition is degree of belief, shouldn't interpretation of HPD interval to relate to users' belief instead of true value? Okay, yes, that's a good point. So the confidence, the HPD, the credible interval, is an interval which we quantify our uncertainty about what we think the true parameter is. We still don't know, but it is a interval that we have to describe our uncertainty about that parameter. And yes, in the true sense of the language, we don't know what the true value is, and yet and HPD, or credible interval, doesn't have this thing called coverage probability, in the sense that if you construct confidence interval just by how the definition of frequentist probability, you are guaranteed, central limit theorem and whatnot. I mean, sorry, sampling theory or not, you guaranteed that you will cover the true parameter 95% of the time in repeated experiment. Bayesians don't have that coverage probability. That just means that you can construct many HPDs or credible interval, and you don't cover the true thing at all. The Bayesian response to that is, well, we don't really know, but it is the interval by which we use to quantify what we believe to be where the parameter should be. So yes, I agree with you, Jerry. That is what you say is correct.
Okay.
Yanni has a comment on Minitab has routines for 2P, Weibull, and other distributions. I think refer to our presentation on the different likelihood.
Yes, but you have to see. Yeah, what I recommend is that you really look at the documentation and you see which are exact and which are approximation. Most of them are approximation. So for example, for the gamma, they use the square root, the cubic root transformation. For the Weibull, it's also an approximation. It's exact for the normal, log normal. So there's nothing for the beta distribution, for example. So be careful that when you're using that product and those calculations, that you know that most of them are approximations, okay? And they do have it, but you just have to find it on their website, okay? So people may get the wrong impression that, oh, I'm getting a confidence interval for a lot of logistic and it's okay. Or a tolerance bound, but they're approximations. Okay, let's show you, yep.
Yeah. I just want to go over some of that. I think I do fast. PT, I don't understand or do we need to consider a prior pre-using posterior? I'm not sure what that means. In other words, we do not need to worry. I didn't understand the question. Okay. Brian asked in other words, we do not need to worry about multiplicity. Okay, this is a tricky part.
This is something, I think we do. This is something that we can handle later.
Okay,
you know?
we'll talk about this later. Okay,
because we're not specifically talking about that right now.
Why normal gamma historically? Yes. Okay. Which size version of this? Why do we seem to Monte Carlo? What did we not specify? Optional is not okay. I think we've answered all the questions.
Okay, good. Yes, no, we'll tackle the multiplicity later. I mean, we're not dealing with that issue here. All this has nothing to do with multiplicity. Just computing a mean standard deviation.
I think Brian's point is that if I were to construct multiple functions of parameters and I infer on the probabilities, and I think there is a multiplicity, but this is a tricky thing, you know, with Bayesian. Some don't. I mean, it depends on if you go read Gelman's paper. But anyway, it's a large issue. Let's just for now bypass it. Go ahead.
Okay, so we're gonna continue now. We did the normal distribution. Let's look at something that we deal with: count data, so visible particles, or in this case, is some data from Krishnamurti. And the reason I'm using this data is because, as I mentioned, they provide a closed form approximation for a tolerance bound equal tail tolerance bound. And this is example 4.4 in that paper, and that's the data. So you have some defect counts some zeros, 1, 2, 3, and some fours, and the mean of that is about 1.66. And if you're dealing with count data, you normally use a Poisson distribution. So what we're going to do is we're going to use a Poisson distribution, and since the Poisson distribution has only one parameter, which is lambda, we're going to put a diffuse prior on lambda. Again, we're going to generate the posterior distribution for lambda, and then we're going to calculate the quantile. In this case, we want a 95% confidence, 90% coverage upper bound. So in this case, we're going to get the 95th percentile of the posterior distribution of the 90% quantile. Okay? And these are the numbers. Okay? Again, in this case, you get the same number. The frequentist approach is, if you use the approach by Krishnamurthy et al., you get 4. If you use the Bayesian with the diffuse prior, you get also 4. Again, same level of comfort. This is the diffuse prior on lambda. It's proportional to the square 1 over the square root of lambda. And this is what I was mentioning. You know, there was this discussion about having some guidelines to interpret the priors. I found this very, very helpful. This is an old document. You can still find it on the web. We have the reference. It's called a catalog of non-informative priors, and we use it a lot. So they have it by situation. So for a beta distribution, they give you something. For a Poisson, they give you something. They give you a reference prior. They will give you the Jeffreys prior and many different situations. So this is, again, how we envision this, that for different types of responses, that we know what an appropriate distribution is, then we know the class of priors that we can use. So here we're grabbing the one from this catalog. This is a situation that we mentioned. This prior is improper. However, the posterior is proper.
Yeah, this is important, and that's why you go read the papers. And the category of a non-informative prior by Berger and Young is actually, it's just really just a formula of a prior that you can use. So we find to be a good reference of the prior.
It is a good prior. And then here is the MCMC code.
Yeah, the MCMC code fairly. Now the thing is a lambda prior is because this is a lambda raised to the half, and negative half is not a standard prior. So you take the log, and which is negative half times log of lambda, and you put that as the functional evaluation of the prior, and then you say low equal to 0, just means that, hey, it had got to be greater than positive. We're not considering. But from a computation perspective, this low equal to 0 is not necessary in PROC MCMC, because even the Markov chain has walked to smaller negative values of lambda. That density variation, that prior variation will return a missing value because it's not valid. If you take a log of negative value, it becomes invalid, and the procedure will reject that Markov chain move anyhow. So the remaining two things is so that's why I said lower equal to 0 is not necessary, but for presentation, if you want to read the program and understand the support of the prior distribution, we recommend that you put it in just so that you understand the model specification. And then
exactly, is that piece of the transparency of how generating the prior, because that parameter has to be greater than 0. So it's a good thing to do. Doesn't take long to add that.
Yeah. And then the Poisson function call, the quantile, is the same, covers 90% quantile. So
yeah. So again, this is a quantile function in SAS, and the first parameter of that function is the distribution that you're using. The next parameter is the coverage. In this case, it's 90%. And then the parameters of the distribution for the Poisson is just lambda. Again, very easy. We're giving a prior to lambda. We're estimating the likelihood there. Counts are distributed as Poisson lambda, can be approximated Poisson, and then we do that to generate posterior sample. And then here, notice we're monitoring lambda and the upper quantile. The diagnostic plots, they look a little funky for the upper quantile.
Yeah, the diagnostic plot is that's because the density estimation is mostly instead of should probably be a histogram, but it's a continuation KDE on a discrete parameter space. But from the trace plot, you can see that it does only take discrete values in that sense. Of course, since it's a transform, it's not part of a Markov chain per se. QU, the Markov chain on the lambda, the trace plot of convergence diagnostic of QU isn't necessarily a very informative thing to have. The density estimation and the counts is what matters. So
yes, so the parameters of the likelihoods that they're estimated. Well, that's the key thing. But we just want to show you that. And these are the effective sample sizes and the Monte Carlo.
Are the lambda in parameter and the prior different thing with same name? Are the lambda in parameter and the prior? Can you go back to the code in the MCMC code? I think someone has a question. Oh, it's the lambda. The lambda are the lambda in parameter and the prior different thing with the same name. They're the same thing. This is a lambda in the Poisson likelihood parameter, the lambda, and then the lambda in the prior. Okay, so the general function is negative log of lambda over 2. So that just means that evaluation of the prior on the log scale. Well, you see on the diffuse prior on lambda is pi of lambda is proportional lambda to the negative half. So it's the same thing. It just means that giving me that lambda value, what's the corresponding prior evaluation on the log scale.
Exactly. So remember, we're doing the Bayesian approach. So we have a likelihood, which is Poisson lambda. So now we're going to put a prior on that parameter lambda. So that's the information that we bring in. In this case, it's a non-informative improper prior. But yes, it is the same thing. This lambda here, this is the likelihood, Poisson lambda, and now we put in a prior on that lambda. And this is just gives PROC MCMC just a starting value for that parameter. What happens with PROC MCMC, if you're using the general statement to write out your own likelihoods, then you have to specify the parameters. If you're using a general thing like the normal and all that, then PROC MCMC is very flexible and takes care of that. So, but yes, they are the same thing. Again, that's the connection between the prior and the likelihood.
Okay.
And then these are, again, the numbers 9.
Effective sample size and the Monte Carlo standard error. Yeah.
9,000, pretty good, and 0.01, they're very small. Yeah. So what happens if you have subvisible particles? Something that, at least for me, I imagine that for some of you it's the same case, the Poisson is not a good approximation because what happens is that the variance is greater than the mean. In the Poisson, the assumption is that the distribution, the mean and the variance of the Poisson are the same, they're the lambda. But in a lot of count data, we observe something that is called overdispersion. And that's when the variance is greater than the mean. In those cases, we use a negative binomial distribution, And one of the things we mentioned last week is in this Bayesian analysis, the parameterization that you use is important. So some of you may be familiar with an alternative way of writing the negative binomial, okay? With the combinatorial numbers and all that. This is thinking of the negative binomial as a gamma Poisson mixture. So what happens is you have a Poisson distribution with your lambda parameter, and then that lambda parameter has some variation around it described by a gamma distribution. It's like a pseudo Bayes stuff, you know. When I look at this and I think of mixture distribution, in a spirit, it's kind of like doing the Bayesian thing because you put a distribution on the lambda. If you look at the gamma Poisson mixture parameterization, is that where gamma here is the gamma number, okay? So this is the gamma number of count plus phi, and count is the response, and then this is the probability of success, and this is a phi parameter. But in this parameterization, your mean can be written like that, and that's lambda. And now your variance can be written like that. So your variance, you can write that as lambda times q. Remember, in a Poisson, the mean and the variance are the same, they're lambda. In the negative binomial, your variance is greater than the one in the Poisson, that's the q. And the q is called the overdispersion, and it's 1 over p. You can write it like this. And if you write it like that, what you see is that if that phi parameter gets large, then that number goes to 0, and then q is 1, then you have no overdispersion. Those of you who are familiar with dealing with overdispersed data, you know that there are tests on Q to test for over dispersion. You know, just essentially looking at see if that how close is Q to 1. If it's close to 1, then the Poisson approximation does a good job. If not, then you use a negative binomial. So again, we're going to use that parameterization.
We can get a posterior of it too. So it's you can look at it.
Yes, we can get a posterior of any of these quantities, and that's the beauty of the Bayesian stuff. That's right. So here, this is a data set that I was presented with many years ago. What do you notice? 4 observations. So you know that you're going to run into some issues if you're going to generate any type of interval with 4 observations, because the confidence intervals, tolerance intervals are proportional to your sample. The sample size, if your sample size is small, those intervals are going to be a little wide. But that's the data that we have. So what can we do with this data? We're going to use, again, that parameterization, and we're going to use diffuse priors on phi and p. Okay? And we are going to compute the tolerance bounds using the posterior distribution of the quantiles. There is a way of doing this, the frequentist approach. There is a way of getting a tolerance bound for the negative binomial. That's something that I developed many years ago and that we use internally. And that, if you use that, you get a number is 4,455, pretty large number. If you use the diffuse priors, then you get 3,883. And you can see the lines here. This will be the frequentist bound, and this will be the Bayesian bound. Even without any information, the Bayesian approach improves, quote unquote, the upper bound in the sense that it's a little closer. One of the things that a lot of you are familiar with is that the agency doesn't like limits that are too small, too close to the data, or limits that are too large. So the reason we're getting a 4,455 is because the sample size is small. But this is just to show you that you can use these techniques to compute a bound that it's not an approximation, and it improves this. Later on, when we're getting to prior knowledge, we're going to see how we can use prior knowledge from other molecules to get a bound for this, and we'll show you the techniques that we use. But again, it's just to show you how to use this with count data. Okay, so these are the diffuse priors. On P, we're using a beta 1,1. That's the same as uniform 0,1. And you've seen this picture before. That's the Fan calls it non-committal. Any value between 0 and 1 is a suitable value for that probability. The mode of that is 5. And for this one, this is a dispersion parameter. Okay, the phi is a dispersion parameter. Remember, the over dispersion is a function of phi. So phi being a dispersion parameter, we use a gamma distribution. Again, this is a recommendation to use a gamma distribution for variance components and dispersion parameters. Same idea as before, you see that, and Fang explained why this is that way. And this is the code. We have the parameters of the negative binomial, the probability, and the phi. We have the priors, the gamma for the phi.
I muted myself. Was I talking?
Go ahead.
Yeah, I was going to, before I go through the code, I want to also echoing what some part of the discussion before is that in this particular case, it would actually make a sense probably to do a sensitivity analysis, is meaning trying different prior distribution and then to see whether upper bound changes from the slides before, whether that's pushing what aspect of the prior distribution on the probability on the phi would move the needle where the tolerance bound lands. We didn't do it, but just in light of someone just mentioned the sensitivity analysis, we would see that's a valid thing to do. And it might get tricky to say how if Jose can go back one more slides. One more slide. It's the value of 3883 changes, maybe not necessarily reporting maybe the range of changes to see different priors being used, and to give people or the agency a sense of where we are not using a very informal prior just so that we could get a so-called improvements on the upper bound in that. Okay, so that's.
And then, yes, and one thing that we mentioned here is we're having diffuse priors on P and phi. One thing that we try, we're not showing the results. You can define a joint prior. These are kind of sort of independent priors, not quite, you'll see that they're not, but you can define a joint prior on P and phi, and that could be also part of your sensitivity analysis. I agree that this is what situation because your sample size is small. Yes.
Yeah, exactly. For the sample size small, and Irina has a question. With only 4 data points, would you not want to go with the wider limit to be safe? Okay, so I think that this boils down to 2 questions. One is how well the likelihood actually fits the data. If it describes the data to the best of the knowledge, we estimate the parameter. However, the limit is we don't know what is larger and what is to have a larger bound implies a certain amount of a limiting asymptotic results based on 4 data points, which I don't think just because it's large it makes sense. And secondly, it's a question of whether the 4 data points fits the likelihood, the negative binomial likelihood, do a reasonable job in explaining the data, even though we have only 4 data points. And then and how the impact of the 3883 as a result of different prior opinions on it. Yeah. And that's the thing about Bayesian being transparent, is that there's only so many things that's involved in it, and we are not assuming we would have 50,000 more data in the future, and now we only see 4, and we know if we see significantly more asymptotically would be such, and then we pull back and then estimate the upper bound. Yeah. We are just saying that this is a question of likelihood, it's a question of the prior, and then coupling them, that is the inference that we are doing.
Yeah, but there's a third point here, and we'll deal with this once we get into part 3, is your prior knowledge. This is a molecule that is similar to other molecules, so you've seen subvisible particle data a lot, so you have a sense for where it should be. And we'll show you the use of prior information in this example, and that will change that. Granted, if you only have 4 data points, then it's tricky, but what we're showing you here is how we can use this Bayesian methodology for that. Yeah.
Should there be data checks on priors? Yeah, possibly. It's really checking on agreements on data, and then based on different prior, but implies different model. So there could be, yeah. But with only 4 data points, you only can do so much. And I mean, I guess the point that we're trying to make is that the alternative isn't any. I mean, just because you could do frequentist approach, just because you can bridge into infinity, there's a huge amount between 4 and infinity, which I don't think necessary to be more reliable just because of that. And the Bayesian represents a higher level uncertainty in the posterior distribution, reflects what we want. You have only 4 data points. We don't know a whole lot. That's it. Yeah, sorry, just one. I know we are running late behind. I think the code is what this code is. That's prior, and then there is a general likelihood is in using the programming statement to construct the negative binomial likelihood that we want of that particular. So you want to talk about it? You can.
Yeah, so you can see here, this is the parameterization that we show you, and here this is essentially that. So we're taking the log of this is the log of the count plus 5 minus the log of the count plus 1, which is this term here, the log of 5, which is this term. So you essentially write out your log likelihood, and you define that as a general distribution, and that's this term there.
Yeah, and then the remaining is just reparameterizing the lambda, the phi and the prob into lambda and q, and then the prob and phi that is used in the negative binomial quantile function in data step. So that's why
exactly, and this is exactly what you mentioned, that we can get q. Q
yes,
is a function of lambda and phi, remember? So we can just write that out, and then we get q. And then we monitor lambda, phi probability, and then the overdispersion parameter, so we can study the overdispersion for these. And these are the posterior distribution for phi and p, and they're correlated, and we'll show you that. Again, that's negative binomial, and p is the probability of success, which is written as 5 over 5 plus lambda, and these are the parameter estimate. So you can see for overdispersion, the estimate of q is 334. So that's far, far, far away from 1. So we do have overdispersion. The other thing to notice here is that the probability here is so small. Okay? And again, once we get into prior knowledge, we will see, we can compare these estimates with estimates we have from other molecules, and we can see, you know, where they fall. Again, those are the effective sample sizes. You can see now that they're not like in the 50,000s, but still, we have 2,000, 7,000, 2,000, 4,000. We're still pretty good.
Yeah, the only thing that the only two things here we still is in lambda and the phi though, right? Because they are the parameter that's being phi and the prob is what the not lambda, sorry, phi and the prob is convergence diagnostic.
Yeah.
They're in the thousands, and that's good. That's good enough.
Yeah, 2,000, that's pretty good. And then they're correlated, and that's the bivariate of 5 on the x-axis and the probability in the y. So see the distribution.
Some researchers calculate the lower tolerance bound, 95% confidence, 95% coverage, and the upper bound to get a two-sided tolerance interval, 95 confidence, 90% coverage. What do you think?
That's not quite right, and we are going to deal with the two-sided intervals next week. We're we'll show you how that is done within the Bayesian approach, and we'll discuss the difficulty of getting two-sided intervals. It's been solved in the normal case, but you cannot just get independent limits like that. Okay, so we'll get into that discussion next week. So one last example we're going to show you is with viability data that can be approximated by a beta distribution. Again, showing you the breadth of the scope of the Bayesian methods and MCMC. So this is viability data. To my knowledge, there's no frequentist approach to calculate a beta-based tolerance bound or interval. Okay, so one thing that people do, they calculate, they forget about this and say, okay, no, I'm just going to use a normal distribution, and I'm going to calculate a normal tolerance bound based on the normal. Just put it through jump, put it through SAS, PROC capability, there you go, you get a lower bound. Or some people get a little more sophisticated, they know a little more, and they say, you know, I heard that if you take the logit transform, you can get the normal data. I mean, you can take this type of data in 0, 1. If you take the logit is a normalizing transformation. So we're in the normal now, so we use the normal approach to compute a tolerance bound, and then we transform back. The problem with that is the back transformation may not guarantee an exact bound. That's only in the case that I know of with the log transformation for the log normal and maybe the Weibull. So your back transform for the logit may not be quite right. So we can just, you know, use the beta distribution and calculate the bound directly using the Bayesian methodology. Again, we gotta have a beta likelihood. Now we have 2 parameters, alpha and beta. So we're gonna put priors there, diffuse on both of them. We generate the posterior distribution. Again, the same approach. And since we want the lower bound, we're gonna get the 5th percentile of the posterior of the 0.135 quantile. Again, we're using the 99.865 coverage because we want to get a 3 sigma equivalent bound. These are the diffuse priors on alpha and beta. We're using the Jeffers prior. And this one, again, comes from the catalog. And this is interesting because the Jeffers prior as you know, is the square root of the determinant of the Fisher's information. And that Fisher information is quite a quantity. I don't think Sir Ronald Fisher imagined the many ways that quantity is being used, not only in statistics, but in other areas. So that is the Fisher information there. And if you take the square root of the determinant, you get that prior. And again, this comes from that catalog. It's very helpful, again, if you have a beta distribution that can approximate your data, this is one prior that works well, and this is the prior that we use. In this case, the code here, the parameters, and this is the Jeffreys prior.
Yeah, this is really non-standard get. So you just have to compute and know the basis of the SAS function that you're able to do. That's all with it.
Yeah, exactly. But if you know SAS, again, we're assuming that you know a little SAS and you know programming in SAS. If you know SAS, then that's that. And the thing is that SAS has a lot of functions. So SAS does have the trigamma function, which is that function that is part of the Fisher information. This PG function here, I forgot to mention. The PG1, that's the trigamma function. Okay?
There's one more thing I would like to point out. The general prior is using the L prior as a function evaluation, and it's a joint prior on both alpha and beta. So, and the reason why it's joint function on prior on both alpha and beta is because you see that in the L prior statement, both alpha and the beta are in this prior evaluation. So you do not want to use prior alpha as general, prior beta as general. This is a way to define a joint prior distribution on both of them. So something to remember. That's all.
Exactly. And again, showing you the flexibility and showing you, this is a little more complex. What we've done so far is you show separate priors for the phi, separate prior for the PROC. For the normal case, we had a separate prior for mu and a separate prior for the variance. Here, we're using a joint prior, and it's specifying the function. Again, if you have it, if you have the equation, you can code it and define it. And then the quantile, again, is the same function, but the beta distribution is part of that. So as I mentioned, the list is large. It's a lot of distribution that you can compute quantiles for. Again, and then we just pass the alpha and beta from the MCMC, and that's it. And then the variability, that's the likelihood. It's a beta with alpha and beta. Okay, that's all. We get that, and that's the calculation. So we're going to show you three things. So if you forget about variability being approximated by a beta, you say, no, forget about that. I'm not going to follow that. I'm just going to use the normal. You get a limit of 0.948, and that's where that limit is. Okay. I mentioned that the other thing that you can do is you can take that data, take the logit transform, which is take the data, divide by 1 minus the data. Remember, this is a quantity between 0 and 1, and take the log of that. This is called the logit. Okay. The logistic regression comes from there, and you can get a limit because that supposedly is close to normal. Do the normal approach and then transform back. You get a limit which is 0.929, and that's the limit there. You can see it. So the normal is close to the data. The logit is far away from the data. And if you do the beta Bayesian, then you get a number that is 0.939, is somewhere in the middle. So again, these are the discussions to have and show. This is sort of a not a Bayesian sensitivity analysis, but we're showing you this to compare the different approaches. Sometimes in our experience is that if you use the normal approach, the limit is too close to the data. And remember, if you're using this limit for process control, anything that is going to be below 0.95 is going to trigger an alarm and an NC. And then that could be a lot of issues. So people are very careful on how they define process control limits. For example, the limit of 0.929, that may be too low, okay? So the Bayesian limit is somewhere in between. Okay?
Sorry, there is
so I think we stop here. No.
there's a question about the code. Can you go back to the
Okay,
code?
let's go back to the code. Yeah.
So the question is, why is there this begin no data and no data block where all the prior definition is in code in case between them? So this is a bit understanding of how PROC MCMC works, or SAS works in general. There is a final via data set, and the SAS by and large evaluates observation by observation. There is an implicit looping behind the scene, goes from the top of data set to the bottom data set. And in that, going through observation by observation, just the same as the data step. In observation by observation, then there is functional evaluation that carries through in the program that you see, just same as the data step. The data step is applying to every single observation unless you specifically tell it not to. The begin no data and end no data is a way to save redundant calculation, because the calculation in them only involves parameters and functions of parameters and not data dependent. Therefore, they don't need to be repeated multiple times. It's like every time MCMC goes through the entire data set, it's the same number of alpha and beta. There's no need to compute the quantile function at each observation. And that's the it doesn't change the answer, but it just makes it slightly more computation efficient.
Yes. Okay. Thank you. Yeah, people are paying attention.
And you did a joint prior because of a high correlation between alpha and beta. No, not quite. So there's two issues right here. One is you can do independent prior on alpha and beta, but we did a joint prior on alpha beta because this is from the category of the prior from Young and Berger, or the Jeffreys prior on alpha and beta. We just want to demonstrate how that can be done as a prior. And there is correlation between alpha and beta, and you can in fact use independent prior on them a priori, which is fine. But the correlation coming from the data coming to govern how alpha and beta would be, and that's a posterior correlation. Just because you have independent prior would not make the posterior correlation go away. So these are two.
And we show these. Yeah. We show this in the negative binomial with the P and the phi, that they were correlated even though we had independent priors, quote unquote. Remember?
Yeah. So that's it's already 12:57.
Yeah.
So maybe we should just stop
yeah,
here.
No, this is it. We're stopping here. We're stopping here, and we're gonna restart on next Friday. We're gonna show you how we're gonna calculate an upper bound for some limit of detection data that is left censor. The LOD is left censor, and we're gonna use a log logistic distribution. So again, it's not easy to do this from the frequentist point of view, especially if you have sensory. We have time for a few more questions.
Yeah.
We can stick around after one, but this is where we're gonna start next Friday.
Okay. There is a question on how does PROC MCMC compare to WinBugs in terms of performance and ease of use. Okay. So this is this depends on how software is being done and what type of model that is used. WinBugs is a standalone procedure that came out of the UK back in the 90s. Bugs is Bayesian using Gibbs sampling. So they do Gibbs just means they do one-dimensional update mostly all the time. And the WinBugs is the window version of the software. It was been very, very popular software. It is very flexible, can do a lot of things. The way that we express how you form a model is different. They rely on a graphical directed acyclic graphical model to say that you have to express your statistic model in a graphical way, and it's all about linking the nodes and so on. So if you are familiar with how to represent it, in most statistic models that we know of fall into that category. If you're comfortable with that, then the software works well. But it's a standalone software that's not part of a high-level statistical software, not part of R, not part of Stata or so you need to so there is a interaction kind of a thing. Is you call the software, it goes off to do something, and you put it back, and there is data processing thing.
Yeah.
PROC MCMC on the other hand, embeds within SAS, but does not rely on graphical model assumption. That's because the requirement on the data step evaluation. So if you're familiar with SAS data step language, transition to PROC MCMC is easier than you would transition to Winbugs. In terms of the speed and the performance, when it comes to Bayesian, there's only two things that's involved: the ability to process at a low-level language, how fast you can process a likelihood evaluation. It's compiled language, which is the same on both sides. And then the second thing is a sampling algorithm. And then there is a pros and cons. You know, some sampling algorithm works better in some situations, some worse than other. It's hard to compare. But PROC MCMC is being threaded and so on, and so it's being actively developed. That's all.
Yeah, and from I'm a SAS user, as I mentioned last week, you know, completely biased over SAS. And so being in the SAS environment, so to speak, for me, you've seen a lot of graphs that they're not produced by PROC MCMC, but you get the data out of PROC MCMC and you can generate, like that plot we show you of 5 and PROC, the correlation plot, that heat map from SGplot, or some of the histograms, or you can use PROC KDE after the fact, you know, because you're dealing with distributions and stuff and densities. You can use PROC KDE to estimate some of those densities after your PROC MCMC runs. And so, and you'll see how we'll show you some other SAS output.
Just two quick questions. Do I need to ask for slides after each session, or can I get all when asking at the end? I think you can get all when asking at the end.
You can get them all at the end. And one of the reasons we're not giving you the slides beforehand is because we work on it, on these, so we have updated versions.
Yeah,
we have updated versions all the time. So, you know, we were even emailing updated versions this morning at 7:45 our time, Eastern time. So that's why if we send you something, we may change something or something like that. But these you can request, and then, you know, you can request them at the end, and then the secretary, Mahalia, will make sure you get them.
I am not a SAS user, but this might be a question. The put the quantile in the posterior function in front of the likelihood function will affect the final results or not? No, it will not, because the function variation doesn't impact that particular function variation doesn't impact how the likelihood is calculated. And since you are now in the quantity of the quantile results in the likelihood calculation, then the order doesn't matter in this case.
Yep.
So that's it. I think we are 2 minutes over.
Well, we're 2 minutes over, yes, again, but if you have any other questions, we may stick around for a few minutes. If not, have a great weekend, and we'll connect again Friday, and we'll continue with the tolerance intervals. The one-sided ones will go a little faster, but we'll show you some other examples, and we'll get into variance component, and we'll address the two-sided intervals.
All right, thanks all. I hope we have answered most of the questions, but if we haven't, maybe you can retype and just let us know, and we stay for a few more minutes and we can answer them.
Thank you all.
Thank you. Okay, I think we are probably good. Most people are leaving, and I think if we
yes, they're down. Yeah, I don't think we have any more questions. So,
all right,
okay,
that's good. So let's see.
Great, thanks, guys. I'll send you the breakdown after the webinar.
Okay, sounds good.
Okay, thank you, Mahalia.
Have a great weekend.
I'll give you a quick call.
Yeah, thank you.
You too. Thank you so much.
Bye bye.
All right,
I'll give you a quick call time. Thanks.
Sounds good. Bye.
Bye bye.